Hi, this is Group 20, and today we will talk about the professional social matching. Today we will focus on the task of the system, and the problem of algorithmic matching involves risks of strengthening the human bias. And how do we solve the problem of role differentiation between human and computational reasoning in PSM decision? To begin, let me introduce the task of this system. It is a system that matches individuals or groups for vocational collaboration and co-creation of value. And it is based on computational approaches to profiling actors, modeling their qualities, analyzing their mutual social suitability and relevance, and presenting the recommendations to the user. But why is computational support necessary in PSM? In order to get fruitful collaboration and high innovation capability results, people need complementary viewpoints among a diverse group of actors. But most of the time, people will choose to interact or work with people who have the same interests or similar ideas. In other words, human decision can result in suboptimal collaboration and untapped co-creative potential, particularly in knowledge work and creative industry that demand cross-pollination of ideas and perspectives.
Now we are going to talk about the opportunities for computational PSM. In this part, we anticipate that PSM is able to solve the following matchings. Firstly, we can use future PSM to identify optimal combinations of professional characters and focus on specific activities. Second, future PSM might recommend partners for co-creative goals, such as business or mentoring field. Third, optimizing team formations for a particular project could be solved by future PSM. What's more, appropriately identifying complementary actors for networked value production is also might be dealt with PSM. Finally, in the future, PSM could be applied to balance supply and demand of job market by advising trainings or new job openings. Next, I would like to turn to the topic of difficulties in computational PSM. In order to build PSM systems, technologies such as item recommenders, social network analysis, and machine learning have to be considered. However, directly utilizing analysis to PSM is likely to produce new risks with damaging influences on performance and cooperation of knowledge workers. First, recommendation is not equivalent to prediction. Therefore, recommender algorithms cannot enhance biased human behaviors. For example, using previous examples to fit training data in machine learning. As McNee said, the recommendations that are most accurate according to the standard metrics are sometimes not the recommendations that are most useful to users. If we insist use recommendation as prediction, it might be against their actual collaboration needs. Second, when we talk about social machine learning, it usually looks for similarity as high as possible. However, when it comes to job market, such matching would lead users to follow the trend to seek similarity. Third, in relationships among social networks, the most common new connections built on actors that are share a strong relation, which form a triadic closure. People are more likely to make new ties with the ones who they know better. However, this narrows one's horizons and decreases divergent thinking due to lack of exposure to new information. Besides that, PSM cannot be generated only across individuals or similarity. An excellent professional matching is decided by actors' current demands, interest, personality, and availability for cooperation. Last but not least, PSM needs a systemic view to avoid Matthew effect. That is, recommending extra cooperation chances for the people who have already got enough relations, while underestimate other important requirements.
In order to advance the future design towards socially meaningful and ethically sustainable design direction, in the article, they have proposed 4 high-level goals for the future generations of PSM systems. Here is an overview of the 4 goals. To make sure everyone understands this concept, I'm going to introduce a little bit more in each one. The first goal is balance diversity and similarity. Similarity is useful when the aim is to validate idea or methods that there is a need for agility in short-term collaboration. Strong common denominators can also open mind to appreciate individual differences. Diversity is beneficial in developing novel ideas with the help of complementary perspectives. Establishing long-term business venture utilizing complementary social capital or making well-informed strategy decisions based on diverse knowledge. In this case, the successful collaboration requires mutual trust and shared working cultures, as well as openness for change and different perspectives. The second goal is enable experience of social serendipity. Social serendipity can be considered as a strong experience of both unexpectedness and instrumental benefits from social encounter and collaboration. The unexpectedness can arise from encounter with people outside one's conventional social circle, or with seemingly different quality than oneself. The element of benefit can result from collaboration that provide value beyond what one could personally attain. The third goal is support a systemic perspective in defining ideal matches. Matching algorithms should not be only optimized matches for an individual user but also consider what is ideal on a systemic level. While social link prediction is typically based on relationship on the local scale, PSM system introduce an opportunity to intervene the evolution of social network to optimize for systemic diversity. Furthermore, the actor's independency demands bidirectional optimization. Matches that are optimized only for an individual can create collaboration proposal with asymmetric benefit and thus remaining inefficient or be rejected. The fourth goal is support the utilization of the existing social structures. In order to advance the system, PSM developers should take advantage of existing social structures in organizations. First, existing weak or dormant ties can be reintroduced through recommendations. Second, diversity-enhanced matching should enable making use of existing echo chambers by identifying potential pairs of actors that are able to connect and bridge the follow knowledge between established clusters, as in the Figure 3. A related matching strategy that contributes to system-level diversity is individuals that can serve as proxy in introducing disconnected individuals or facilitating new coordinate between connected individuals.
This part is about PSM system qualities and future directions. This figure outlines a high-level system architecture with key modules and their main functions. These are related to an analytical pipeline as well as general system qualities that need to be addressed across the presented modules. We can see on the figure there are 4 qualities that they consider important for future PSM systems. The first quality is sensitive for professional context and purpose. It is challenging to find the balance spot between maximal diversity and similarity. It is context-dependent target. Moreover, an understanding of current social structure is needed to identify meaningful configurations of matching logic. So, the article says that PSM developers draw from the diversity bandwidth trade-off theory to navigate the design space. The context forms a mixture of several individuals and organizations' contextual characteristics. Formalizing the contextual variance requires new methods and frameworks that conceptualizing PSM in more details. PSM development needs to carefully consider which practically available data can best support the context-specific analytical goals and how to compensate missing data. There are two alternative design strategies to enable context-sensitive in PSM system. One is reactive design. It leaves the active user in charge of driving the system in a way that contextual requirements are met. Another one is proactive design, follows the logic of prescriptive analytics where the system suggests actions or even takes them on behalf of the active user. The second quality is multi-dimensional analytics. Research shows that relevance of recommendations and usefulness of recommender system increase when multiple different recommendation strategies are in parallel. For example, Hooper discussed the advantage of multi-dimensional social network recommenders to increase interdisciplinary collaboration. Although this approach can help identification of relevant matches, it still needs to consider additional perspectives. For example, geographic distance must be considered, especially in long-term collaboration. In addition to axiomatic data availability issue, defining the logic in which different analytical functions are combined in context-sensitive manner requires research. PSM can affect by a broad range of human features. All of them cannot practically be embedded in algorithm design. It needs multidisciplinary research collaboration.
The third quality is user-system cooperation for decision support. Due to the complex nature of PSM, they argue that the matching decision cannot merely be automated by algorithms. For example, machine learning generally produces relevant results only if initialized with good quality training data and well-defined goals. This figure shows the potential collaboration points along the computational analytic process. First, it needs methods that guide the user to selecting appropriate training data and analytic goals to enable accurate profiling and predictions. Semi-supervised approach could allow training with a very small amount of labeled training data, minimizing both the cold start problem and the need of manual work by the user. Second, it needs feedback from the user regarding which factors are the top priority in the current matching case. Third is need to support user exploration, which has been found to be important in visual network analytics. Well, the previous section revolved around how the user steers the system. User-system cooperation also touches the system's influence on the user behavior. To address the goals regarding optimal diversity, they expect that end users need to be nudged away from their habitual and individually oriented preference in networking. The notion of diversity-sensitive design can be considered to reduce that trust issue in exposing users to the diversity. Matching people and interests are already enabled by various digital platforms and social media. However, nowadays there are few solutions that would take a more explicit and proactive role in social matching. PSM calls for technology that should take a more active role that has its own judgment to optimal matches. The conventional way of enabling content recommenders, such as adding randomness to the result, might not be enough for PSM system. In order to avoid bias and prejudice, they use ranking and rating encode human bias, which making the presentation of matches focusing on qualitative description rather than numeric ones. Persuasion can also manifest itself via the facilitation of forming the connection. For example, in an event, context is low-risk in matching. The matched actor can be given a playful challenge to explore their commonalities and complementariness by not revealing the exact reason behind the recommendation. Finally, proactive systems for PSM pose new challenges for user systems as they manifest design ethics beyond the will of a user, which is the traditional fundamental in human-computer interaction. The computational design ethics would be need to balance between the individuals' preference and the greater good of organization or other social entities.
To conclude, we outline the complex problem space of professional social matching, and we define design goals for computer-supported PSM and requirements for developing next-generation system. Thank you everyone for listening, and if you have any question, you can ask now. This is the citation.